we shall consider a new model of computing, namely DNA computing. It is a new paradigm and it is one of the models of natural computing. So, if you look into the different branches of natural computing, you can divide them like this: models inspired by nature, that is bio inspired computing. Under this comes neural computing. You know that nowadays neural networks play a very important role in the field of computer science, and they have come into existence because of the simulation of brain. In neural computing, you try to simulate the way the brain works, and the neural networks are implemented with the electronic silicon computer. So, the implementation is through the electronic media. And you also have what is known as an evolutionary computing, genetic algorithms. They try to solve an algorithm making use of representing an instance using a bit string, and then they perform the operations of crossover, mutation, selection, etc., which happens in the actual evolution of humans or any other organism in nature. And because they simulate the evolution, it is called evolutionary computing, and genetic algorithms come under this. Genetic algorithms are mostly heuristic algorithms, and even though they are heuristic algorithms, in most cases they give very good solutions to some problems because they converge. Even though the convergence cannot be properly proved, in most of the examples where it is considered, it is found that by taking the model in a suitable manner and representing the strings in a suitable manner, the convergence can be achieved. Even for network algorithms like routing, etc., evolutionary computing has been used, and it is a very good area of research nowadays. You also have what is known as swarm intelligence, ant colony paradigms, and so on, which are biologically inspired. In contrast to that, you also have some models which simulate nature and show how nature is being developed, like fractal geometry and cellular automata. You might have heard about the game of life and so on, how it is done with cellular automata. That is the second one. The third one is actually computing with molecules or computing with natural objects, that comes under molecular computing. The actual thing is the molecules and how they behave and interact with each other, giving solutions for problems, and that is called molecular computing, DNA computing, peptide computing. They all come under this, and the implementation is really using the DNA strands or the peptides and the molecules. So, the implementation is through biomedia. In 1998, the paradigm membrane computing was proposed because it tried to simulate the behavior of what happens in a cell, the proteins, the enzymes, the membrane structure, how they develop, they pass through the membranes, changing from one form to another and so on. And initially the theoretical model was developed, and the first paper in this area was published in 2000. At that time it was thought that there are two possibilities. One, it could be implemented using the silicon computer like the evolutionary algorithms and so on. The other one is we may actually use membranes or cells and try to simulate the algorithms. This was the question in 2000, and in 2010 now this looks that it is not possible at all, how to make them make the algorithms be simulated by actual cells, whereas this looks more promising. That is, this may develop as a bio inspired model of computing like evolutionary computing or neural computing, and will be implemented in the electronic media only. Molecular computing or DNA computing is implemented via biomedia. And what is the motivation for this? You talk about mathematical biology and biological mathematics. What is this? In one way, mathematics tries to help biology, and in another way, biology tries to help mathematics or computing. The reason or the comparison between these two models is that the biological mathematics is a simple observation that the following two processes are very much analogous. What are the processes? The very complex structure of a living being is the result of applying simple observations like copying, splicing, etc., to initial information encoded in a DNA sequence. Simple operations continuously applied gives rise to many things, and that helps the behavior of the DNA strands. DNA evolve, and the basic operations are cutting and splicing, cutting and pasting, splicing, etc. In mathematics, you can look at the function computed. Anything should be computed. You can look at it as a function f computing something. W is the input and Fw is the output. The result Fw of applying a computable function to an argument W, the result given is Fw. It can be obtained by applying a combination of simple functions to W. Even though f may be a very complex function, it can be obtained from simple functions by continuous applications. This is the definition of partial recursive functions. Any function, any computable function, you can define making use of the initial functions and then using the operations of composition, primitive recursion, and minimalization. Okay. So, these two processes are very much similar, and the similarity between them tells the connection between mathematics and biology. Mathematics has always helped biology in forming hypotheses. In stochastic processes is one of the things which helped biology a lot, and you try to form hypothesis giving the theoretical background and verify the hypothesis. The other question is, can biology inspire mathematics or can biology help mathematics, and that is answered by DNA computing. Actually, the DNA strands or biological material is helpful in doing some computation. That is what we are going to see. And one way to look at it is, any Boolean circuit can be formed from the 3 gates and or not. In fact, 2 of them is enough. So, basically if you have AND or NOT gate, any Boolean function can be implemented. Similarly, some basic operation will help the DNA strand to evolve in any manner you want. This initially may look a little bit puzzling and you may not accept it, and this was the situation earlier about 40 years back when somebody said 1010, it meant 1010, and it did not mean number 10, right. So, the binary representation people were aware of, but it was not very familiar. Whenever some number is stated, they really thought it is base 10. But now when somebody says 1001, immediately the mind will grasp it as 1001 or 9, number 9 with the base 2. Base 2 has become part and parcel of our life with the invention of computers, but it was not so about 40 years back. So, that is what I want to say, that is today DNA computers may look something new, something not acceptable, but after 20 years it may become a part and parcel of our life. This is the current situation, and in DNA computing you want the whole computation to be done like this with DNA strands using biomolecules, using test tubes and so on. But at the current stage this is not completely possible, involving lot of cost and time. We want to do everything in a very quick manner using less cost, and that is not possible today, but it may become possible after some time. But how much it is going to be possible is a question, it is still a question. But finally we may end up something like this, because the operations have to be performed manually, it may take lot of time. You may use some DNA strands, but then the operations may be performed by a robot, which is really a silicon computer. So, you may have a mixture of both electronic media and biomedia and end up with a situation like this, where things can be done in a much efficient and in a fast way. So, what is DNA computing? The first paper or the first work was done by Edelman in 1994. He tried to find out whether a given graph has a Hamiltonian path, and he developed a new algorithm for that using DNA strands and experimentally verified that, and that was a breakthrough result. And after that a lot of experiments and lot of research is going on in this area. Now, coming back, what is a DNA? DNA is deoxyribonucleotides, and it has got a sugar part of it, a phosphate group, and consists of a nitrogenous base. It can be divided into two groups, the purines and the pyrimidines. The purines are adenine and guanine, and they are represented by the letters A and G. The pyrimidines are thymine and cytosine, they are represented by the letters T and C. RNA is ribonucleic acid. Now, the splicing system was defined, that is, the DNA can be used to model some behavior. Recombination of the DNAs can be modeled by using what is known as a splicing system. This sort of a theoretical work was done by Tom Head in 1987 itself. But in 1994, when Edelman published his paper, then only lot of interest was created in this area, and this is one of the reasons for the development of formal languages and automata theory. New models of generating languages have been defined, like splicing systems, sticker systems and so on. So, what is a DNA? DNA is a double stranded, it has a helical structure and it double stranded. This was found by Watson and Crick, for which they were awarded the Nobel Prize. And T always combines with A and C always combines with G, they are called complementary pairs. So, A always pairs with T, G always pairs with C, and there is a double hydrogen bond between them, A and T, and a triple hydrogen bond between C and G. So, the structure of a DNA is something like this. You have a sugar part and you have a base part. This will be different, A, G, C, T, and the phosphate part, and the carbon molecules are named as 1, 2, 3, 4, 5. So, this is called 1, 2, 3, 4 and 5. So, you can see that A always will combine with T only. T has a structure like this to represent in a pictorial form, and A can only combine with T, A cannot combine with C or G, and C and G only can combine. So, you can see that suppose I have one single strand AGCA, then I can put this TG here and it will become like this, properly matching, and here for G I should have C and for A I should have T, and so this can be brought here, and then I am having a sticky end here. So, it can be combined, this is a double strand and there is a sticky end at this portion. This helps to form the second strand if you know the first strand. Suppose I have a lengthy DNA single strand, and then the second strand I do not know, but I have several pieces of second strands, and which one will match with this? if anything is allowed, it will be very difficult to match, whereas the Watson-Crick complementarity helps us to form the second strand in a very convenient manner, and this is the basis. This and immense parallelism is the basis for all DNA algorithms. So, with that you can form the double strand in a very convenient manner, and you see how easily this has been formed. Also, the double strand is represented like this. One strand is represented as 5 dash to 3 dash end, another one is represented as 3 dash to 5 dash end. So, you have the 5 carbon atoms. The last one here with a phosphate structure, it will combine with the third one here, and so on, like that these A, C, G, they will be combined by bonds like this, and here again 5 will combine with 3 and so on. So, this one is called denoted as 3 dash to 5 dash end, this one is denoted as 5 dash to 3 dash end, and these always pair together. There is a double hydrogen bond between A and T and a triple hydrogen bond between C and G. So, the operations which is usually done on DNA molecules, they can be classified like this: separating and fusing of DNA strand. DNAs are double stranded. By heating they may become single stranded, and by cooling and adding ligase they may join and form a double strand. Single strands can join and form a double strand. Lengthening of a DNA, given a DNA strand you keep on increasing the length. Shortening, cutting of a DNA using a proper enzyme at the restriction site, and two DNA can be linked together using ligase, and nucleotides can be modified a little bit. Then you can increase the number of DNA strands, multiply them, so that helps in identifying the proper strand. The multiplication of DNA strands, or it is called amplification, it is done using what is known as polymerase chain reaction. A double stranded DNA is given like this. To get 4 strands from this, it is a single double strand. From this you can get 2 double strands in the following manner. You heat it to a proper temperature, so the double strand becomes single strands, and you add what is known as a beta primer and a gamma primer. What is beta primer is the complement of the few nucleotides here. When you add and then use polymerase chain reaction, this will keep on forming the second strand, and the whole thing will become a double strand. Similarly, adding a gamma primer here, that is the complement of this portion here, and this will be lengthened and you form another double strand. So, from one double strand DNA you can get 2 double stranded DNA. If you repeat the process, you will get 4, 8, 16 and so on. So, after some time the number of double strands will increase, and this is very essential in some operations, we shall see that. And reading out the sequence, there is a specific way you can read out the sequence of the DNA. We will not go into that. Sanchez method and other methods are available for that. Another operation which is performed on DNA molecules is to separate them by length. For that, what is known as gel electrophoresis is used. Here in a table or in a tray, gel is used, and with a comb a little small pits are made, and then the DNA is poured into this. The solution containing the DNA strands is poured into that, and then a current is applied. Here you have the negative and here you have the positive electrode, and after some time the strands, they try to move in this direction, and when they move in this direction you find that the longer strands move slowly, whereas the smaller strands will move very fast. So, small strands will move fast and long strands will be moving slowly. So, by calibrating it in a proper manner, you can select DNA strands which are of a particular length. Suppose I have strands of length 80, 120 and 160 say, then I want to choose only strands of length 120. I apply the current in this gel tray, then this will be shorter strand 80, this will be 120, this is 160. So, in this portion I select and take the corresponding DNA molecules. So, this is called gel electrophoresis. So, smaller one you use polyacrylate gel, and for the larger ones you use agarose gel. And how do you note it? You can stain with some fluorescent object and then detect where they are. Anyway, those are details of biochemistry, and we will not go into that, we will more look into the algorithmic part of it. Now, Edelman performed an experiment first in 1994, and that was the starting point for this subject or this new model of computing. And what he took was a graph, directed graph, and the problem is to find out whether the directed graph had a Hamiltonian path. So, the practical possibilities of encoding information in a DNA sequence and performing simple bio operations were used by Edelman to solve a 7-node instance of a directed Hamiltonian path problem. What is a Hamiltonian path? A directed graph G with designated vertices V in and V out. V is the initial vertex, V out is the final vertex. It is said to have a Hamiltonian path if and only if there exists a sequence of directed compatible one way edges E1, E2, E3 etc., that begins at V in and ends at V out and enters every other vertex exactly once. So, this is the graph he took. There are 7 nodes 0, 1, 2, 3, 4, 5, 6 etc. There is a directed edge between 0 and 6, there is a directed edge between 4 and 5 and 3 and 2, 1 and 3 and so on. The input vertex is V in is 0, the final vertex is 6, that is V out is 6. Does there exist a directed path from 0 to 6 which passes through all the other vertices exactly once? You can very easily see that in this there exists a path 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. In some graphs you may have more than one path like that. In this particular graph there is only one path, one Hamiltonian path. The question whether a graph has a Hamiltonian path is an NP complete problem. So, it does not seem to have a deterministic polynomial time algorithm, but using DNA strands you may solve it in linear time, and that is what we want to see. In a naive manner, to find out whether there is an Hamiltonian path from 0 to 6, you arrange the vertices 0 to 6 in the order, first one should be 0 and 6, and in between the 5 vertices you can have any permutation. So, there will be 5 factorial permutations, and each one of these permutations you can check whether it constitutes a directed path from 0 to 6. This is an exhaustive search and it cannot be done in polynomial time. Now, the algorithm he designed for this problem was like this. This is not the usual type of an algorithm. It had 5 steps. Step 1 is you generate all random paths through the graph, and then second step will be keep only those paths that begin with V in and end with V end. Third portion will be if the graph has n vertices, then keep only those paths that enter exactly n vertices, including the initial and the final one. Then the fourth step is keep only those paths that enter all the vertices of the graph at least once. Then the fifth step is if after all this any paths remain, then you say yes, there is a Hamiltonian path, otherwise you say no. What we mean by a random path is like this. See, for example, 0, 3, 2, 3, 2, 3, 2, 3, 4, 1, 3, such that is a random path. 0, 1, then 2, 1, 2, 3, 4, 5, 2, that is another path. Like that you may have several paths. So, first of all we have to generate all such paths, and in those paths some path may be like this from 4 to 5, then 2, then 3, then 2, then 1, you may have a path like that. But we want to find out the paths between 0 and 6, that is the path should start at 0 and end at 6. That is the second step of the algorithm. Keep only those paths that begin with V in and end with V end. And the third step is if you have n vertices, the length of the path should be n. So, 0, 1, 2, 3, 4, 5, 6, the length is 7, right. Then you must make sure that it passes through each one of the vertices of the graph, and then finally check whether there is a path which satisfies all these criteria. Now, how it was done using DNA strands is like this. Now, each vertex of the graph was encoded into a random 20 nucleotide strand of DNA. Then for each edge of the graph, a DNA sequence was created consisting of the second half of the sequence encoding the source vertex and the first half of the sequence encoding the target vertex. By using complements of the vertices as splints, DNA sequences corresponding to compatible edges were ligated, that is linked together. Hence, ligation reaction resulted in the formation of DNA molecules encoding random paths through the graph. Let me see. See, he took S2 like this, that is the sequence of 20 letter sequence representing the vertex 2, another 20 letter sequence representing the vertex 3, another one representing the vertex 4. Then there is an edge between 2 and 3. How is this edge represented? It is from 2 to 3. So, the second half of S2 is taken, this portion, and the complementary sequence is taken. For G the complement is C, for T it is A, for A it is T, for T it is A, and so you see that the first portion of the edge is the complement of this portion, whereas the second portion is the complement of the first portion of this G C T A, complement should be C G A T. So, you see that this portion C G A T A A, this represented the complement of the first portion of vertex 3. So, similarly, there is an edge between 3 and 2 starting from 3 to node 2, and how is this edge represented? It is represented by a 20 letter sequence or 20 nucleotides. The first 10 will be the complement of the second part of S3. This is the sequence for vertex 3. The second half of that is this, the complement G, A, etc. will be the first part of this, and the complement of the first part of S2, which is ATA, this portion, that will be the second portion of the vertex from 3 to 2. Similarly, the edge from 3 to 4 can be defined by a 20 letter sequence. So, what he did was all these DNA strands which are of length 2, which are of length 20, they were taken and put in a test tube and ligases added so that they could join together. So, suppose there is an edge, there is a vertex S2 and this is a single strand of letter 20 letter sequence, and S3 is vertex 3, there is an edge between 2 and 3 that will join here edge 2 to 3, and suppose there is another strand S4, the edge corresponding to E3 to 4 will come and attach like this, because the first portion of it is the complement of the second portion of S3 and so on. So, strands like this will represent paths. What does this represent? It represents an edge from 2 to 3 and then 3 to 4. Okay. So, by mixing all the strands together, all the strands which represent the nodes and also which represent the edges, you form double strands of this form, which will represent all sort of random paths through the graph. Now, among that we want to select those which begin with V0 and end with V6, node 6. How do we achieve this? Edelman used the following criterion to do that. The second step he implemented in the following manner. The product of step 1 was amplified by polymerase chain reaction, and there the strands using proper primers, the primers will determine where they begin, right. So, by using V in and V end as primers, it was amplified. So, finally, you ended up with only paths which begin with V0 and end with 6, that is node 0 and end with node 6. How is the step 3 implemented? Step 3 is you have to make sure that all the paths are of length 7, or because a node is represented by a 20 letter sequence, here the DNA strand should be of length 140. 7 nodes should be represented by 7 into 20, 140, length 20, length 140. So, for implementing step 3, a technique called gel electrophoresis, that we have seen what it is, and you put all random paths, all DNA strands representing random paths and use gel electrophoresis and select only paths of length 140, that is the length of the path is 7 in terms of the nodes. So, you apply an electric field and larger molecules travel slowly. After a period, the molecules spread out into distinct bands and you choose only those of size 140. The next step is you have to make sure that the Hamiltonian path passes through every vertex of the graph. So, you have seen that it begins with 0 and it ends with 6, but how do you find out that it passes through 1? For that you use what is known as affinity purification. The complement of vertex 1 is taken and attached to a glass bead. The whole solution is passed through that, and wherever the sequence corresponding to the complement of node 1, I mean the node 1 sequence attaches with the complement attached to the glass bead, and so the rest of them will be washed away, and this strands you collect after a little bit of heating. So, this process, affinity purification is the process, permits single strands containing a given sequence V to be filtered out from heterogeneous pool of other strands. After synthesizing strands corresponding to complementary to V and attaching them to magnetic beads, the heterogeneous solution is passed over the beads. Those strands containing V anneal to complementary sequence and are retained. Strands not containing V pass through without being retained. So, after doing this, you slightly heat the solution. So, these single strands will come out. Then you make sure that the same thing is applied for vertex 2. So, that only strands containing the sequence corresponding to vertex 2 remain. Then you make sure for vertex 3, then vertex 4 and then vertex 5. That way you make sure that all strands are of length 7, I mean in the terms of nodes it is 7, in terms of DNA strand it is 140. Then it passes through V1, it passes through V2, it passes through V3, it passes through V4, it passes through V5. That way if it starts in 0 and ends in 6 and passes through 1, 2, 3, 4, 5, then it must be a Hamiltonian path. Now, do you have a DNA strand which satisfies all these conditions? How do you test it? In the last step, if at all the solution contains some paths, some DNA strands representing paths from 0 to 6, then that must give you the answer yes. But then in performing these operations, the number of DNA strands may be reduced. So, to make sure that you detect all the paths properly, you again apply polymerase chain reaction to multiply, to amplify. If you have 2 or 3 strands, by doing this you may end up with 30-40 strands, and so there should not be any problem in detecting that. So, if at the end you have some DNA strand remaining, that will represent a Hamiltonian path. This way Edelman showed that a Hamiltonian path problem, which is an NP complete problem, can be solved using DNA strands. The main point to be noted here is that all the random paths are parallelly generated. There is immense parallelism, and that is what is helpful here. Also, we can see that the Watson-Crick complementarity, that is A joins with T and C joins with G, and that helps in doing all these experiments and designing the algorithms. After Edelman designed this algorithm for Hamiltonian path, Lipton came out with an algorithm which is somewhat similar to this for the Boolean satisfiability problem. You know that Boolean satisfiability is the first problem to be shown to be NP complete. So, for that Lipton came out with an algorithm, we shall not go into that. Afterwards, several problems they found that can be solved with proper DNA algorithms. The DNA algorithms are basically different from the ordinary algorithms. So, initially there was lot of enthusiasm that a biochip can replace a silicon chip and everything can be done by a biocomputer, and at least to prove it theoretically everything can be done by a biochip or a DNA computer. You have to show that the Turing machine can be simulated with that. This has been done. It has been shown that the operations of a Turing machine can be simulated by a DNA computer. There were two models, one is called the Beaver's model and another is called the Rothman's model. This model seems to be a slightly better model because it does not involve step by step simulation, but the whole thing is simulated in a full. Now, this is about the DNA computing. initially there was a lot of enthusiasm that the biocomputer or a biochip will replace, but afterwards the enthusiasm slightly came down because it is not going to help if for multiplying two numbers it is going to take 50,000 rupees and 3 days. Okay. So, you are not going to do that. So, the cost involved and the time involved are not so helpful in this, but in future something may happen, developments may take place in biochemistry and lot of improvements can take place. So, the things can be done in a much quicker and less costly manner, and sometime for at least for some problems the DNA computer may prove to be very useful. Whatever it is, in formal language theory, lot of theoretical developments have taken place because of this. New models have been defined for generating languages. One of them is the splicing system, which I will briefly see what is a splicing system. Actually, this model was defined in 1987 itself, nearly 7 years before Edelman published his work. Another model is sticker systems, and in the automata side you have the Watson-Crick automata, which deals with double stranded strings, which I will just have a brief look at what is a splicing system. The recombination of DNAs or recombinant behavior of the DNAs is used here. You have double stranded DNAs like this. This is one double stranded DNA, another double stranded DNA. You may have a restriction site here, an enzyme may find a restriction site and then cut it at the proper place. For example, take these two sequences, you have a restriction site here, you have a restriction site here, and then the enzyme when you apply it may cut it in a proper manner like this. So, the first strand is cut into two pieces like this and the second strand is cut like this. Now, you find that you have ACG here, you have the same ACG here and so on. So, this portion can join with this and this portion can join with this when ligase is added. So, DNA fragments are formed like this. Then when you add the ligase, this joins like this and this joins like this. So, in the end you get two other strands. This operation is called splicing and formally it is represented as a splicing system. The abstract model is defined like this. Instead of using the DNA strand, you use any string over an alphabet, and two strings analogous to DNA strands. You have one string W1 as W1 dash U1 X V1 W2 W1 2 dash, another string W2 which is W2 dash U2 X V2 W2 dash. Then you see that in the middle you have U1 X V1 and you have U2 X V2. These triples have taken as restriction sites. These can be looked at as restriction sites here. This is the way Tom had defined, and because of his name such systems are called H systems, H schemes, etc. The latter definition they do not make use of that X, whereas generally an alphabet V is considered and the rules, splicing rules are represented like this: U1 hash U2 dollar U3 hash U4, where hash and dollar are two special symbols and U1, U2, U3, U4 are symbols or strings over the letter V. This is called a splicing rule, you call it as rule R. So, it is of the form U1 hash U2 dollar U3 hash U4, some of them can be empty strings also. So, they are strings over V star, and given such a rule you have 3 strings x, y, z. From x and y, by applying the rule R you get the string z by splicing. If the following happens, you have x as x1 u1 u2 x2, y as y1 u3 u4 y2, and the rule is this. So, a cut can be made between u1 and u2. So, here you can make a cut here, and similarly you can make a cut between u3 and u4. So, you can make a cut here, and then the first portion x1 u1 can combine with the second portion here to give you x1 u1 u4 y2. So, the situation is like this: x is of the form x1 u1 u2 x2 like this, then y is of this form. By the rule is this, please note that the rule is u1 hash u2 dollar u3 u4, that means a cut can be made between u1 and u2. In the second string the cut can be made between u3 and u4. So, with this you will find that the cut is made here, the cut is made here, and the first portion x1 u1 combines with the second portion u4 y2 to give the string x1 u1 u4 y2. You could also have this portion combining with this. In the formal definition, these two have a slightly different, one splicing, two splicing you call them. Anyway, this is only a brief introduction to the splicing system, and we are not going into the details of the definitions. So, what is a splicing scheme? A splicing scheme, it is denoted by a sigma. It has an alphabet and a set of rules. The alphabet is, it can be anything. In the case of DNA it will be double stranded A, G, C, T, etc. R is the set of rules which is of the form over the alphabet V plus etc., V star, it can be lambda also. Hash denotes the cutting place, dollar separates the first string from the second string. The set of rules, it is called the H scheme. Why H? H, there are two reasons. One is this: when you have these two strings and the cut is made and you are joining here, this is like a H turned 90 degrees. So, here you join, so that is a H turned through 90 degrees, or it is also because of the name Tom Head, who first proposed the formal model. And for a given H scheme, what is the language generated? You look at it as a language generated. You start with a set of axioms or from set, and from them take two strings and combine them, you will get another string. So, the set of all strings formed like that gives you the language. This is single iteration. In general you can do it several times. So, you have iterated splicing. Anyway, that definition is also I am not going into the details. That is called a H system, and then you can distinguish between total alphabet and target alphabet and call as extended H systems. So, a splicing system is a triple. V is the alphabet, L is the set of strings with which you start, and R is the set of rules, and they are represented like this. They can be finite or infinite, and we can look at them as regular, context free, etc. With this you generate the language. Let us consider one example. The example here is this: you have the alphabet A and B, and the rule is A hash B dollar B hash A. So, in the first string the cut will be made between an A and B, in the second string the cut will be made between a B and a A, and you start with the language A power n, B power n and B power n, A power n. So, if you take any A B B A, you will get A A, because the cut will be made here, the cut will be made here, and the first portion will combine with the second portion here. Similarly, if you take A squared, B squared and B A, the cut will be made here, because the cut has to be made in the first string between a and a B. In the second string, the cut will be made between a B and a A. So, this A squared will join with this A to give you A cubed. Similarly, we can get any string, and you find that any string of A's can be obtained for n greater than or equal to 2. So, the language generated by the system starting with this language, the language or the axioms with which you started this, with this if you perform single splicing operation, it is not iterated splicing, but it is just only one splicing operation, then you find that you can get this particular language. You can also look at it as computing a function. Look at this ABC alphabet, rule is of this form, cut is made between A and B, and the second string cut is made between C and A, and you start with x as a power n b and y as c a power n. Then if you take a string of this form, the cut will be made between a and a b. In the second portion, the cut will be made between a c and a. So, the first portion a power m will combine with the second portion to get you a power m plus n. So, actually it is performing addition. If you have m and n in unary it is represented as a m times, in unary number n is represented as n a's. So, you get the addition in unary, it performs addition in unary. For example, the say taking this a power 10 b and c a power 5, you will get a power 15. How is this obtained? This goes here, this goes here. So, a cut is made between a and b, a cut is made between c and a, and this joins with that to give you a power 15, which is the addition of 10 and 5. The other portion c can combine with b, but we do not bother about that. So, you can even look at it as computing some function. And what are the limitations and main considerations in DNA computing? The main considerations are time and cost. As I told you, if it is going to cost you 50,000 rupees and 3 days to perform the addition of two numbers or multiplication of two numbers, it is not worthwhile doing it. But this may get improved over the time, because when the first computer was built, it was very big and it occupied some very big hall. But now you find that you have very small computers, you have laptops and so on. So, the time and the cost involved in that may become, time may improve and cost may come down, but that may take some time. The second one is more important. There may be a lot of errors because of practical errors involved in doing the experiment. You know that when we consider the Hamiltonian path problem, we assume that all the random paths could be formed, and when we performed the gel electrophoresis, proper strands could be chosen and so on. But there may be error that you may leave out and so on. What types of error can creep in? Two types of errors can creep in. One is you may miss out some strands, that is very dangerous. Sometimes you may not select the proper strands you want, sometimes you may select unwanted strands. Selecting unwanted strands is not so serious, because next step they may get discarded, but not selecting wanted strands is serious because you may miss out. That is why from one step to another step when you go, In order that you may not miss out the strands, frequently you perform polymerase chain reaction and amplify. So, when you amplify, the number of strands here get more and more strands you get, and so the chances of losing out a correct strand will be less. Another type of error which can creep is unwanted annealings. That is, I want something to get attached like this to one strand, I want another string to get attached like this, whereas this strand may be like this may come and attach somewhere else. That can happen only if you do not choose proper sequences. The sequences should be chosen properly. Suppose I cannot take A 20 times, because that may create problem. Any subsequence should not have 5 A's or 5 T's and so on, and also something should not get repeated. If you follow certain rules like that, these errors could be minimized. And as I told you, it looks that it may not be really useful in every aspect, but on certain aspects it may become very useful. They are associative memory, that is, lot of information can be stored in 1 cc of DNA strand. A DNA strand can store a lot of information, and within a few cc's of the solution we can show. If they are taken a single strand, one portion may represent the address. It is something like the address is here and the data is here. So, when I want to fetch the data from here, if I add a complementary strand for the address, I want to fetch the data which has this particular address. So, the complement of that can be synthesized and added to this solution, and you pick out those strands with this address, then you can find the sequence and find out the data from that. This may take time, but anyway the fact to be noted is it can be done in a proper manner, and also within a small space you can store lot of information, and again with the improvement in biochemistry this may be done in a very short time. Another one is DNA to DNA computing. In many cases there are tests to be done on DNA. A crime occurs and you want to find out whether the blood there is the same as the blood of the culprit, and you suspect somebody to be the culprit and you want to test his blood. So, sequencing is done, DNA test is done and so on. In many other cases also, in finding out the crimes and legal battles, finding out the DNA sequence becomes important, and for that if you use the ordinary computer it may take a lot of time, whereas for such operations DNA to DNA computation, if you want to find out whether a particular subsequence is present in a DNA strand, instead of making them as strings and then testing for the presence of the substring, if you really use DNA computing, this may work out in a better manner, and also within a short time you may be able to compute it. So, in these cases DNA computing will be really useful. A third application is cryptanalysis. When you want to break a crypto code, if you take DES has become very old now, you have other details now, but older one I am mentioning, data encryption scheme. You use 56 bits as key. This is the old scheme. New schemes you use 128 bits and so on. So, 64 bits of block, a block has 64 bits, it will be encoded as another 64 bits, and there are several steps involved in that. using the key. Now, with 56 bits there are 2 power 56 possible keys, and if you want to find out the key one by one you have to test. Anyway, I am not going into the details of this. This can be done in a very efficient manner using DNA computing, because you can test whether a particular bit string is a key simultaneously for all the 2 power 56 keys. We can test it simultaneously. So, the time involved will be very less because of the immense parallelism used in DNA computing. So, even though it may not work out well for all problems, particular problems like this or particular applications like this may find DNA computing as a very useful tool. Time only has to tell us whether such a thing will happen and how far it will become useful. But whatever it is, it has generated lot of interest in formal language and automata theory by the development of new models like splicing systems, sticker systems, and Watson-Crick automata. There are other models like Watson-Crick L systems and so on. So, this development in DNA computing has enriched formal languages and automata theory.